This is the Q&A webinar, but we're going to start off going over the different types of 3D printing and how they're being used currently. We're going to use some coronavirus related case studies to kind of put things into context for everybody, which should be a little bit of fun. So to the left is myself, and I'm also joined here by my colleague Tom, who's going to be talking about some of the more technical aspects that we're going to be going over today, and probably taking the weight off my shoulders and answering some of the more difficult questions.
Okay, thank you very much, George, and good afternoon to everyone. So, as George said, what we're going to do is we're going to run through some of the more basics around 3D printing, build up a little bit of knowledge just so everyone who's joining us today in this webinar is on the same page. And then what we'll do is we'll make our way through, use some case studies as well, before moving on to the questions towards the end of this webinar. So to start off with, the three most common types of 3D printing processes, you've got your FDM, SLA, and SLS. FDM being your fused deposition modeling, or fused filament fabrication. There's another term also used for that. That's going to be your kind of hot glue gun on rails. Then we've got your SLA, your stereolithography. That's going to be your resin. This can be cured by a laser. And then lastly, selective laser sintering, your SLS, which can be a powder base. As I said, we're going to work our way through, give a bit of an understanding about what these three different processes are. So let's move on to the next slide. Starting off with the old SolidWorks slide. So firstly, what we're going to have to do for most of these processes is get a hold of the file type, which is going to be an STL, or in most likely cases, also do have 3MF files as well. So your STL you can get out of SolidWorks pretty easily. File, save as type to STL, and you can see it turns it into thousands of different triangles, which is then readable by the middle ground, the slicing software that's used for the printers. So that's kind of the basics of getting a hold of the file. Now let's hop back across and have a look at the printers themselves. So FDM is where we're going to be starting off with. So for the FDM printing, what you're going to need to know is a bit of an understanding about the process itself. So how do we actually print the file? Well, I mentioned then about the slicing software, that middle ground. Your slicing software is shown as A on this image. That's where you're going to be putting your STL file in. As soon as you get that STL file in, we can do some tweaks. We can set the temperatures, set the layer heights, little things like that, before pushing across that data as a G-code across to the printer itself. So as I said, this is going to be your FDM, your fused deposition modeling. And what it's going to effectively do, it's going to take a filament spool, push it through some gears. The extruder itself is going to heat it up and push it through a nozzle. Once it's out the nozzle, it's going to go down to the build platform, and it's going to create the part itself, building up layer by layer on the build platform, going from nothing at all into your finished outcome. So your standard FDM printing, it's going to be easy to use. It's going to allow you to kind of print out parts with minimal knowledge or setup. There's lots of things on most of the printers, such as auto bed leveling and kind of the ease of actually loading the filaments, loading that material on itself. So it will allow you to kind of take the printer itself and get up to speed and up to printing really quite quickly. There's also going to be a huge variety of materials available, ones that come from the printer manufacturer themselves. So for example, Sindo, you're going to have your Sindo standard filaments. Ultimaker are going to have their standard filaments. There's also going to be other manufacturers out there that allow you to go into kind of further depths and go into more niche markets and fields.
Also, being able to scale up FDM printing to larger bed sizes is something that's more obtainable, whereas with other 3D printing technologies, it can be a little trickier to print larger scale parts. So if large format 3D printing is something that is important to you, then FDM 3D printing is probably going to be worth looking at as well. So here's a nice way in which FDM is currently being used to battle the coronavirus. So we've been working with a lot of our customers 3D printing face shields. We've been 3D printing them here, but we've also been getting people to send them in. We've been getting about 600 out a day. So the face shield is just to the left there. But also little things to help stop the spread of the virus, like that little doohickey on the door there, which is allowing that chap to open it with his arm instead of his hand. So reason being that we've gone for FDM for that little thing on the door there is that it could be quite a large part, and that you might struggle to fit that on a high resolution resin printer. Also the sort of material that might be required, you might need something that's biocompatible, as everybody's going to be touching it. As we touched on earlier, there are a range of materials available on FDM, so you can get that biocompatible material and run it on the FDM printer, no problem. So on to the next slide.
So thanks for that, George. So just to kind of go for a bit of a quick recap through FDM, your fused deposition modeling. So it's going to be quick and easy to use. As I mentioned, you can plop it on. It's going to have lots of built-in assistances. So things like your auto bed leveling, basically allow you to go through and just get those prints rolling straight away. It's going to have relatively low startup costs. Obviously, it's going to completely depend on what printer is purchased and used. However, the price point for these allows you to kind of hop in, take that, starting with one spool of filament and build it up from there. As I mentioned, these spools of filament, well, there's a wide variety of them available. Maybe the ones that are kind of your closed source, ones created by the manufacturer, as well as your open source, or different more niche materials able to be used. Kind of furthering on that, you can also have the option to reinforce with fiber. This is something that's specifically for Markforged machines, which we'll just run through now.
So fiber reinforcement on an FDM printer will allow you to start making composite parts that are about the strength of aluminium, but 40% lighter. This is a unique feature to Markforged, as the technology has been patented by them, but it's very much where we see the future of FDM going. I'll touch on a couple of reasons why that is the case in some later slides. But you can see to the right here that the base material there is a nylon, and then there's another base material which is onyx, which I'll run through in the next slide. And then what you're actually doing to those materials is reinforcing them with continuous fiber strand. So the best way to picture it is if you've got a concrete structure, you'll have steel rebar running through that concrete structure, which significantly adds strength to that structure. And this 3D printing technology is working much in the same way. Instead of the concrete, you have the nylon or the onyx, and instead of the steel rebar, you have one of your fiber reinforcement materials, which can be either a fiberglass, a Kevlar, or a carbon fiber, depending on what the application of the part is. So on the next slide, just going to show off some features of the Markforged printer. So if you look to the top right, you can see some weights being laid down on some different materials there. So to the right, you've got PLA, which is a very popular 3D printing material. It does print very well, but the strength of PLA generally isn't all that great. It's not going to withstand a huge amount of force. ABS is something that is seen as a little bit more premium in the 3D printing market, but still, even ABS doesn't have the same kind of strength characteristics as onyx. So moving to the top left, we've got a graph here. So down the bottom, you can see the stress strain curve of the nylon, and then the ABS just above that, and then onyx further above that. So onyx is a nylon based material with chopped carbon fiber particles within it, and that's about almost twice as strong as ABS alone. When we start to achieve far higher stress, well, we get far higher up on the stress strain curve graph with Kevlar reinforcement in those parts, and then fiberglass, and then right at the top there, we've got the carbon fiber reinforcement, which is taking us above aluminium. We've got a fun little video down the bottom left there of somebody absolutely battering some parts with a hammer, and the Markforged part holding up quite well. So how is fiber reinforcement printing being used now? So one way in which we can start to make face shields as we move to production 3D printing, and we're trying to mass produce the face shields, is we can actually 3D print tools that can bend bits of steel. As you can see in the video on the left there, there's a press tool which has been 3D printed and is actually bending sheet steel. So I'll just play the video again there so you can see it in action. So we are starting to see people using injection molding machines to start 3D printing these face shields. And you may well think that that's going to start putting 3D printing out of the picture, but that's where the Markforged can shine, because they're a production 3D printer. You know, we can start to make these high strength parts, and you can even start making tooling parts, which can then you can start making products from that tooling. Tom's going to talk through SLA printing next, so I'll pass you back over to Tom.
Thanks, George. So yes, SLA printing, as I mentioned earlier on, slightly different than your FDM, your fused deposition modeling. That's hard for me to say. So we're going to move on to stereolithography instead. So whereas beforehand it was using a filament spool, now we're going to be seeing as a vat of resin is going to be cured. So there's a nice little image on the left-hand side, just running through the basics of that process. So as I said, you're going to have your vat filled with the resin. That's going to be your base material that's going to be used. And then the laser is basically going to cure off just what needs to be created. Therefore, what you effectively end up happening is an upside down process. It's going to start and kind of create itself in the complete opposite way of what you usually expect when you're looking at your 3D prints from the FDM. You also can see as well it's printed on that nice angle. Those angles effectively help it to go through and just create the part and get all the curvatures and all the geometries perfectly smooth. The GIF on the right hand side just runs through and shows you the other part of the process, which is the support material. It's easy to remove, as you can see. There's going to be little touch points that are kind of connecting the part itself to the build platform that's being lowered down into the vat of resin. So that's basically the process. As I said, slightly different, using resin and lasers this time rather than heat and filament spools. So what are the benefits? It's a different process, so it's going to create some slightly different styles of parts themselves. So we'll start off with the materials. So you've got some interesting material choices. May it be your flexible resins, which allow you to have an isotropic unilateral strength across the entirety of the part itself. Therefore, for any rubber seals, you know it's going to have the same strength throughout. It's going to help with the whole sealing process. So as I mentioned, the isotropic parts, that's simply going to be because of the way the process works. Well, it's going to go through, you're going to have the resin being cured by the laser, but that isn't the whole process. You've got a separate curing stage afterwards where it applies a UV light and some heat, which give it the full mechanical properties it needs. So that, as I mentioned, kind of further down, that curing stage can be tweaked. You can get different properties out of the materials themselves. So for example, I'm going to use that rubber as an example again. Well, what you can do is you can effectively either cure it for a shorter or a longer amount of time to affect the shore hardness of it. So other things, you can have your high details and your great surface finishes, simply down to the fact that you can print to a much smaller level. You can print up to 25 micron with certain materials on the Formlabs printers, which we are discussing, which, as I said, not only allows you to get that detail, get that really great surface finish, but also allows you to print a lot smaller. So for those kind of small, more detailed parts where the factor of the nozzle size in your FDM process may be slightly limiting, that's where SLA really comes into its own. So I'll pass you back across to George. Let's have another look through another COVID-19 related study of how SLA is being used instead.
So nasal swabs are something that are starting to be produced now to help out with the NHS testing everybody for coronavirus. So nasal swabs can be printed on an FDM machine, possibly. You would be able to print them on the Markforged machines. I know that Markforged are doing the same, but on the lower end FDM machines, because an FDM machine essentially has a home position, as you get further away from that home position, so further up in the Z axis, the accuracy of the part can start to deteriorate. So printing these long struts in the Z axis, you might see some warping on an FDM print, or just because the plastic is coming out of a nozzle, which usually has a diameter of about 0.4 millimeters, it's going to struggle with those very small amounts of detail. As you can see on the end of the nasal swabs, there's a very fine detailed texture on there, which we're able to 3D print on the SLA printers to capture some of that particulate that might be coming out of people's noses. So nasal swabs, perfect for the SLA machines. Also being able to use the biocompatible resin as well is a big win, which some 3D printing processes might not have access to biocompatible materials. So we're going to move on to SLS 3D printing next.
So SLS, your selective laser sintering. So a slightly different process once again. So this is going to be a powder base. That's what's going to be going through and helping us to actually create our parts. So we can see again that image on the left hand side, just running through the basics of how the machine's going to work. As I mentioned, it's going to have powder inside there. So the powder not only creates the material but also supports it at the same time, which basically allows you to go through and create some really great geometries. It's going to be a laser once again, but this time it's going to be more similar to how you'd imagine a normal scanning would work, whereby it's going to be the entirety of the screen flashed at once. So this does help to give us a very unique property when you're looking at the SLS process. What it means is that batch production can really be maximized. As soon as you put one part into the build volume, the entirety of that height worth is going to tell you, let's say, for example, 10 hours. If you were to fill the entirety of that build volume to that point with the same part, again, as you can see in that kind of top right hand side image, it's going to be 10 hours across the entirety of it. As I mentioned, it's that scanning process you'd imagine on a normal kind of 2D paper scanner. It allows us to go through that one flash of laser, one flash of light, effectively going through and doing the curing for us, allowing us to really maximize it, as I mentioned. And it also suggests that you can go through and you can basically support itself. And what that means is we can have some more complex geometries due to the fact you're not going to have a support structure there that's going to be causing the issues and removal afterwards. So it definitely assists with that process of really making the most out of your printer itself and the materials you're putting into it, without a doubt. Okay, back to yourself, George.
So here's a nice case study that you might have heard of towards the start of the coronavirus outbreak, of some chaps in Italy 3D printing some valves for some breathing apparatus. So the reason that SLS was used here was that there's some very complex geometry, and some of it is internal geometry. As you can see on the top of the valves, you've got that indent, and within there's some geometry. And if we weren't using SLS, we'd probably need to put some support structure in there. It might be quite tricky to remove that. So using SLS is allowing us to print something like that and just blow the dust off, and then we have our finished part. So there are other 3D printing processes out there besides the ones which we've touched on. We've covered the three main ones and the most popular ones, but some of the higher end manufacturers will be using processes like material jetting, binder jetting, SLM. So some of those processes are really useful for creating very high end parts and also producing very accurate prototypes. So here's an image of a ventilator design that's being developed by Lamborghini on the left, and some designs by Ford on the right of their prototyping stage of their take on their ventilator design. So what's going to be really important to you guys when you're listening to all of this is you're going to be thinking, will these 3D printing parts perform for the applications that you guys might have in mind? So as we've kind of briefly gone over, we do have a lot more 3D printing solutions other than the ones which we've shown today. But whether the needs of the parts that you have in mind are, you need very high strength parts, accurate parts, high resolution parts, you need to be working in a very niche material. We have solutions for each of those, and I'm going to quickly go over, before we do the Q&A, how you can work with ourselves in proving out that a 3D printer is going to work for you. So this just quickly goes over our process. So We will start with a lot of data collection from yourself. So we'll focus on understanding the application that the parts are going to be going into. We'll work with yourselves to do a financial analysis, which I'll cover on the next slide, which will basically show that a 3D printer will pay for itself or not. And then we'll work with you to provide you with some design for additive advice on some parts. And then we'll help you 3D print those parts so you can test them in-house, so you're sure that the solution that you have in mind is going to work for the application. So just to quickly run over what a return on investment study looks like. So we would work with you to understand the current costs of manufacturing parts, and then we would compare that to the 3D printed cost of manufacturing parts, and then also compare lead times, and then also look in more detail about maybe how you've faced some issues currently which could have been prevented if you had the 3D printer on site, maybe avoiding production downtime. And we'll basically form a return on investment study off the back of that. So to the bottom right, you can see the graph that has been generated for this customer that was looking to 3D print all their store parts. So the requirements of the store parts varied quite a bit. So we had to deploy a 3D printing suite. So the Markforged 3D printers were used for making some of the higher strength store parts, which were previously aluminium. The Formlabs was used for making things like suction cups, so we could use the flexible material there, but then also get that nice surface finish. And the Ultimaker was used for making some larger parts that needed to be food safe. So we found a bespoke material online that suited that need very well. So they now have a suite in place which is making all of their store parts, which is also able to use for prototyping. And we showed them, if you look back to the bottom right of the graph, that they were going to save money year on year, and basically the payback period was going to be 13 months for this. And that's one of the longest payback periods that I've done an ROI for. I mean, typically they're around 6 months. There can be a couple of months. Depends on the machine and what you guys are looking to achieve. But that's typically a long payback period for a 3D printing solution. So as I mentioned, we will guide you through the functional testing phase as well. So we would offer you design for additive advice on any parts that you sent over and make sure that they're optimized. And then we would 3D print them for you, and you can take them into your workshop and try and blow them apart if they're a Markforged part, if you like. If it's a Formlabs part, you might want to be putting it in front of somebody and discussing, how much like an injection mold it looks. So we're going to run a quick poll now to get a better understanding of what you guys are interested in and what you would like to see in future webinar content. So we're just going to run that now and collect your responses. Just as that's coming in, I can see that there's a good amount of people interested in high strength and accurate 3D prints, and also a good amount of people interested in niche 3D printing materials, and some people interested in high res 3D prints. A little bit less on the large format 3D printing. If you are interested in large format 3D printing though, I would suggest visiting our website and looking at Big Rep 3D printers. So they're our large format 3D printing solution, and they print objects up to about 1 meter cubed in size. So that's brilliant. Thanks very much for that information, guys. And now we're going to have a look at answering some questions. So we did have a question that was sent in just before we started the webinar, actually. So we're going to have a go at answering that one first.
Okay, yeah. So we've got a couple of questions so far, so we'll do our best just to run through all of your comments and see if we can hopefully share a little bit more knowledge. So one of the first ones we had was, what limits do 3D printers have when it comes down to geometries? So your internal corner radii, your overhangs, does it make it more difficult or more expensive to manufacture? So again, this is going to completely depend on the 3D printing processes used for it. So for example, in your FDM, your fused deposition modeling, you're going to have the limit of the nozzle size. I believe George mentioned earlier on, standard, it's usually 0.4 mil. So for example, your layer height is going to be a factor of that, whereby you can print up to 80% of that size before you start encountering some issues. However, if we were to compare that to your SLA process, you can print down to 25 micron layer height, and that's when you can really kind of make the most of it. There are opportunities to improve this when you're looking at the FDM method, however, whereby you can get smaller or bigger nozzles. Your bigger nozzles, you can print out things quicker, but obviously your layer lines are going to be a lot more pronounced, whereby if you do the opposite into that, if you decrease the nozzle size, then you can go through and you can start getting your smaller, more complex and more detailed components. So hopefully that gives you a little more information on that one. So another one as well is, what thickness should parts be to resist fatigue? Again, it's another, what print are you using? So for example, if let's say you're on a mark forged print, there needs to be a certain size, a certain wall thickness in order to actually be able to implement the continuous fibers. So for example, if you had a feature that was about 3.6 millimeters, you can get in a single strand. Then you can also go into creating looped features. So think about having a handle on an object, which should most likely be looped depending on the orientation you're printing it in. You can get that down to about 2.8 mil. So there's definitely design for additive manufacture that you can apply into them. However, more of a general answer to it would be infill. So if you're printing with an Ultimaker or a Cindo, your more standard FDM printers, whereby obviously if you increase the infill to a certain extent, it's going to be the percentage of material that's applied to the insides of your parts. You can increase strength from it. And similarly to that, obviously you can go through and increase your shell layers too. So there's two really good questions to start off with. George, have you seen the other ones you want to have a quick ping through?
Yeah, so we've got one from Jose, who's wondering about the strength of SLA resin compared to ABS FDM printing. So the SLA printers, they don't actually use, say, an ABS or a nylon, but the developers of the SLA 3D printers will develop their own resins to mimic the mechanical properties of existing materials. So, for example, Formlabs, which is our SLA 3D printing solution, they have a resin which is called Tough, which mimics the mechanical properties of ABS. And they also have a resin which is called Durable, which mimics the mechanical properties of, say, a nylon. If you're 3D printing on an FDM machine, the layer adhesion is an important factor. So if you're pulling parts apart in the Z-axis, you might end up pulling an FDM part apart a lot easier than, say, a SLA 3D print, because the layers are chemically bonded together. So it's an isotropic part, so it has better omnidirectional strength. So if you're pulling apart a SLA print in the Z-axis, it should be just as hard to do than, say, if you're trying to pull it apart in the X or Y-axis, whereas FDM prints may be a little weaker in the Z-axis. Having said that, if you're using a high-grade FDM machine, then the layer adhesion is usually a lot better, so you won't encounter so much of an issue there.
Okay, we've seen a couple of questions coming in regarding UV resistance. So two different questions around them that we're really seeing. So firstly is just very much what UV resistant materials are there for outdoor use. So a good one to use would probably be ASA. So ASA is a UV stable version of ABS effectively. So that's going to be the kind of material choice if you're going through and doing just kind of standard FDM printing. When it comes down to Formlabs and SLA printing, obviously UV exposure is what's used to cure the part. However, obviously that's going to have the detrimental effect with especially the standard resins they have of the continual curing over time. So there are quite a few case studies we can certainly run through as well on a later basis regarding this. In general, the standard resins tend to be about a year outside. It does depend on the amount of sunlight it's seeing. If you're based in the middle of Sahara, can imagine the UV exposure is potentially going to be a little bit more than certainly gloomy Britain. When you look into more of their engineering resins they've got available, they see the amount of time they're actually able to last outside increasing. So there's definitely resins of choice for it, more specifically the engineering ones.
So another question that we have is which 3D printing process is more accurate? So I've just got a slight laptop issue. There we go, solved. So Mark-forged FDM 3D printing is the most accurate process at the moment. Reasons behind that are multifactorial, but essentially Mark-forged is an enclosed solution. So the Mark-forged 3D printers have their own software and their own materials. So everything is designed to run together, which ensures repeatability and accuracy with each 3D print. Whereas if you're running an FDM printer, a normal FDM printer, you might be buying different filaments online, and you're going to be ending up with different results and different quality control on those different filaments. So the accuracy of the parts that you're printing on a typical FDM machine compared to a Mark-forged one is going to be significantly different. There's also tools on the Mark-forged machines for ensuring accuracy. So there's something called onboard inspection reporting. So that will actually laser scan the parts as you're printing them, which will give you an inspection report to refer back to. So you can actually mouse over little bits of geometry and see how far over or under tolerance that they are. And just to cover SLA as well, SLA is, you can get a lot of high resolution off an SLA print, very small amounts of detail. Sometimes across a larger print where you've got a big block of geometry, if the curing process isn't quite right, some parts of that geometry might overcure, some bits might undercure, which can lead to slight warping in large SLA 3D prints. So I'd definitely say that Mark-forged is the most accurate and has the tools for ensuring that accuracy as well.
Okay, another question coming in was on the length of time to producing parts. So more specifically, what is the most time efficient one? So I'll definitely go with FDM. Realistically, it's down to the nozzle size. You can increase that nozzle size. You can really, therefore, increase the layers. When you're looking at the SLA perspective, there are options available. So Formlabs have released a draft resin, which allows you to really increase that layer height. To believe it's 300 micron off the top of my head. So with that, obviously, that's going to definitely improve the amount of time. But still, with your FDM being able to go to 0.32 or 320 micron with a standard 0.4 nozzle, obviously, as soon as you start increasing that nozzle size to a 0.6 or 0.8, you can increase the layer height with that. If you've got less amount of layers being created, therefore means you can print it a bit quicker.
So I've got a question about producing a dense, bright white part with very thin wall sections of 0.2 millimeters, typically about 25 millimeters square in overall size. So for something like that, we would be looking at SLA. The only constraint on the minimum feature size of SLA is the laser dot size, which is, do you remember what it is on the Form 3?
It's a very good question.
A few microns. Tom's going to look that up now. But also there's a material available called rigid, which is impregnated with fiberglass particle, which you can print on the Form 3, which would be a very dense white material, possibly very good for that application. So if you are interested in seeing if that is the case, pop us over an email with the file and we can take a look at it with you.
Okay, so other questions we had coming in. So is there a point where aluminium or steel can actually be put into designs? Yes, and is there an easy way to actually incorporate into the printing? Again, the answer is yes. So let's take two printers as an example. Your Ultimaker and your Mark-forged. Both of them have the ability to have a stop at layer functionality inside the slicer itself. So obviously what you could do is you could, on any FDM printer, you could just hit pause. Obviously that's going to be down to yourself, the user, and that's where kind of further issues can come into it. By being able to actually design and slice the software and slice the part inside the software at having that exact layer it stops at, it means that it's paused and it's actually ready for you to kind of drop in the aluminium, the steel, whatever it might be into the design itself, and then continue printing on afterwards. So it's a really nice and easy way to go through and do that.
So I've got another question about are there any materials with repeatable spring characteristics to allow for small quantity spring manufacture? So there's a material on the Formlabs which has recently, don't know, who's it available to, the rebound material?
So it's available to anyone. It's slightly different in the fact that it's not a standard or not an engineering rate. It doesn't really fall into any of the categories that are sold by Formlabs and sold by us. However, we can get into contact with Formlabs. We can get it as a more of a specialist item in. So one of the biggest things you find with a Formlabs printer is that it will automatically dispense resin in while it's going along. This is part of the process where they have to do a lot of development in to make sure that you know that you can leave your printer when you put your print on a Friday afternoon. You can come back on a Monday and it's not going to run out of resin over the weekend. So that's kind of where a lot of the development in the resin actually comes down to. So as you mentioned, the rebound resin, it was initially developed with New Balance to be incorporated in one of their shoes, which you can go out and buy. It's in the sole of the shoe indeed, yeah. So very similar to I believe it's the Nike's Infinity shoes, I remember correctly, where they've got that kind of that spring in the base itself, created by a topology pattern. So yeah, so that's where the resin came from. To answer that question, and yes, you can get a hold of it through us. Just let us know, and we can certainly go into further discussions about it.
So I've got another question about how do you optimize support structure on an SLA 3D print? So with the Formlabs printers, the slicing software that comes with the Formlabs is something called Preform. So within Preform, you have full control over support locations. So each and every support you can toggle the location of. The supports will be auto-generated for you at first when you pop the model into the slicing software, and you can really toggle it from there. Also, little features like the touch point size you can toggle, so the actual area that the support is actually contacting the part, the diameter of that area, you can toggle. So when you snap that part off, you've got less, much smaller little bumps that you might have to deal with. So there's a lot of customizability in the slicing softwares for each 3D printer. So within Formlabs software, you can customize that.
So I've got a question coming here. It says, why do parts warp? And the customer mentioned that they do face this with thicker builds. So warping, you tend to see occurring with specific materials and mainly in the FDM printing process. So let's go through and try and give a bit of an example. Let's say, for example, ABS. You're printing ABS and you're trying to print out a tooling piece that looks, let's say, similar to a brick with some holes in it, for example. It'd be quite a nice example. That's going to be a lot of material you're trying to put into it. And the biggest reason you're going to find warping occurring is down to heat. As it's trying to firstly adhere itself onto the build platform, you need to make sure the heat between the two is actually able to kind of connect it on. If it doesn't have enough surface area, you're going to find warping might occur. There are tools inside slicers to help you out of this. Your brims, your rafts, your skirts, all of those kind of build plate adhesion tips and tricks you can put in are really going to assist. The next question comes down to, as it's cooling when it's being printed, it's going upwards. Obviously, it's naturally going to cool if the heat inside the build volume itself is dropping, or let's say you've got an opening on the front of your printer, cold air is going to go in, ambient temperature is going to change, causing warping, causing cracking and splitting. So there's a few different tips and tricks. If we were going to go into much more detail than that, I think we'll be here for a few hours. But don't worry, there's going to be certainly a video I'm going to be putting up at some point soon regarding this exactly, because it's one that it's very easy to see, but there's also different things we can run through. As I've mentioned a couple there, you can tick off and you can do the tweaks too.
So I've got another question about what sort of materials can you use for mold tools? So depending on the temperature resistance required and what it is you're going to be molding, the solution may vary. But a popular one is the high strength, high temperature fiberglass reinforcement available on the Markforged printers. So the temperature resistance of Onyx should be okay up to about 150 degrees for a sustained period of time as well. And that high strength, high temperature fiberglass reinforcement running inside that Markforged part is really going to help hold the part together and stop it from expanding at all. So that's one solution to the mold tool. Another one would be using a high strength, high temperature resin, a high temperature resin, not high strength as well. I need Markforged for that. A high temperature resin on the Formlabs printer, which is resistant to they changed it recently because there's a V2 resin now. It's a 220 now.
I believe it's a little bit less than that.
Possibly a little bit less, around 200, 220. And the benefit of using that material for the mold tool is that you're going to get that really smooth surface finish that you typically get off the Formlabs printers.
Okay, fantastic. So there's a couple of others we'll keep running through. So how to make sure a design will print in a way where nuts, bolts and fixings will fit first time or with very little prep. So again, firstly, it's going to depend on what printing process you're using. It kind of links into trying to put in aluminium or steel into a design as I spoke through earlier on. Obviously with an SLA process, you're going to struggle, simply because it's inverted. You try and put something in, it's going to fall back into the resin. So it's going to have to be an FDM. So the FDM printing process, if you can get it into a nice location when it comes down to regards of orientations, it can make it a lot easier for you. So if you try and drop a hex nut in and it's falling down kind of face flat with the hole itself of the bolt to be going vertically straight upwards, you know, you can create that hexagon pattern and you can give it, let's say, 0.15 mil gap. That's usually about right. What I then recommend doing is looking to that stop at layer functionality. So you want to make sure when you're looking through that it's just before it closes up. And again, a 0.15 gap at the top is usually quite a nice one. It does depend on what you're using it for, because in most cases, having a little bit of room like that isn't going to inflict the design later on, but it's certainly something that's worthwhile looking into. Again, that's something that we can certainly discuss in further webinars and further videos as well, blogs.
Or just give me a call. My mobile number's there. I love talking about this stuff. So is Tom. We'll probably just carry on talking about it when we finish with the webinar. To be honest, we start talking about see that hypercar that's been 3D printed recently.
This is going to turn into a podcast at some point soon.
Yeah,
it might be a bit of a different format.
They use a topology study to make the frame of the car, like the chassis. And then they 3D printed it in aluminium, and they 3D printed loads of carbon fiber parts in it as well, and it looks pretty cool.
Certainly some interesting automotive applications out there. That is for certain.
Oh, yeah,
big rep, and we've come down to the large format printing that's I believe a few people selected for a later webinar. You'll see automotive manufacturers creating front bumpers and test pieces for wheels.
Yeah.
They can then get an idea of the entirety of the size of it very quickly and very easily.
So we had another question about will using a lower diameter nozzle on a FDM printer help with the surface finish? So it will help with the surface finish, but it's going to help more, I think, creating smaller feature sizes. There is also the ironing feature on the Ultimaker, which gives a really nice gloss finish on FDM prints. Also, in general, on the Markforged printers, the layer adhesion between layers is that good that the parts off a Markforged printer are really smooth to the touch. So that's kind of lending itself to, as I mentioned earlier, the Z-axis pull-apart strength on a Markforged print is far beyond other FDM printers, and it's down to that better layer adhesion. And a nice benefit of that as well is that the surface finish on those parts is also really good too.
Yeah, it's a very good point. A really good question on that one. So again, when you're using those smaller nozzle size, effectively the biggest effect you're going to see is the amount of layers that are required and actually able to be printed over the space of the distance of the part increases dramatically. If you increase the amount of layers you're putting into it, the distance between each layer when it's creating curvature and creating complex geometries is going to be less visible. That's effectively your main thing you're going to see. And that's where obviously your layer lines are going to be quite large if you had a larger size nozzle, but it can be quite small if you have a smaller nozzle. So that's kind of your main factor is really going to help you out there. There was another nice question as well on what filament, what geometry / function. Again, horses for courses. So if you're looking for strength, your Mark Forge with using Onyx with some continuous carbon fiber, perfect. If you're looking for flexibility, you could print TPU on an Ultimaker or a Cindo, or you could print with a flexible resin or an elastic resin on the Formlabs. Good all-round material, let's say using a Ultimaker, tough PLA is pretty good, simulates ABS mechanical properties, but prints about as easy as a normal PLA. So yeah, someone was mentioning earlier the issues of warping. Your material choice can be a massive factor into this. That example I gave of creating that massive block, printing tough PLA would probably be a lot easier and you would get about the same strength. But obviously there's plenty of other options out there and a lot more of the niche materials as well. For example, MD Flex, for example, is quite a nice one, created by, is it Copper 3D, that one? I believe it is.
It is, yeah.
Yeah, so that's a flexible material that has small pieces of copper into it. It's basically going to help to keep it safe. It's going to be used in a kind of applications such as medical, because it's going to clean itself up as it's going along. So it's another fantastic material, and yeah, so there's certainly a lot of options out there for different applications and choices.
So we had another question about are there any books or tutorials available? We do run training courses which you can book yourself onto, and if you've been on a Solid Solutions training course, they're run in a very similar format and you leave with a big textbook. If it is something that you're not able to kind of get out of the office or you're not able to spend any money on anything like that, we are working on an education section on the website at the moment, but I will reply to that and I'll send you some stuff across that should be useful to get you off the ground and get you guys a good understanding of how the Markforged 3D printers work, which we will also be covering in a future webinar. As our poll showed, a lot of people were interested in the high strength and accurate parts, which are typically Markforged parts. So look to the future and on our webinar schedule for anything that involves high strength 3D printing, because we will be going over Markforged 3D printing in that webinar.
Yeah, certainly a good point when it comes down to the getting the knowledge as well for 3D printing. All of these printers that we kind of discussed today out the box do work very easily. It's the small refinements, the small details, the questions such as, oh, what material should I use for this, or what purpose is going to work best for this, and that's kind of where we can, hopefully with these webinars and any emails or calls across to us, we can give people a little bit of extra help, a bit of assistance.
So it is a bit of a minefield out there. There are quite a few brands out there, and it can be difficult to know what is the best solution for the application, and that's where we're here to help, and also provide the tools to show that the solutions that we think are going to work will work, backed up by concrete data collected from yourselves and then put through something like our return on investment tool.
There's another question, I'm not sure if we went through this one yet, but it's whether or not parts can actually be water and oil proof at pressure. So a very good one. So I'll let George go through the Markforged application. There's certainly a good few case studies regarding it. Formlabs, well, what you're going to find, because of the fact that they are printing isotropic, as I said, you're going to go through, you're going to use the resin and then you cure it afterwards, as well as the laser to create the actual shape itself. It's basically going to mean that all the layers in the X, Y, and the Z are formed together. Therefore, you can pass water through without the issues of any of it escaping. We've seen some good applications as well where Different resins have been used for purposes such as the ends of blow torches, and also been used for pressure vessels as well. Obviously, it's going to depend on the thickness. However, again, because of the printing process, we know that it is able to actually pass the water, pass the oil through. It sounds like you've got a really good specific question on that one, so please do follow up with us and we can have a look through for you. Yeah, I did mention the Mark Forged one. So the application for that one, we've seen a fair few pressure vessel testings done with the Mark Forged components.
Oh yeah, so we worked with the RNLI previously, and they did some tests on Mark Forged prints, submerging them, and found that they were fit to go out on the lifeboats. We've also had a customer that's made a Mark Forged part that's a seawater intake, so that's exposed to seawater over a long period of time. So with lower grade FDM prints, you may not be confident in submerging them because the layer adhesion on them isn't all that great. So you might be able to, some water might be able to infiltrate into the print in between the layers, whereas on a Mark Forged print, the layer adhesion is that much better that the parts are fairly safe to be used in a submerged environment. We've also had some customers like kind of aluminium coating FDM prints. So if you're looking to 3D print pressure vessels in particular, do get in contact with us and we can forward information on about that. But it is a little bit more of a long-winded technical explanation that might keep us here a while. So yeah, do get in contact about that though.
Fantastic. Well, I think we've gone through the majority of the questions. If you do have any other ones, please do contact us on the email provided and the number provided on the PowerPoint right now. If not, drop us an email or a call through on the main number for Solid Solutions. You can get through to us as well. And if you do have any further questions, please do let us know. It's been hopefully we've been able to give you some assistance, run through some of your questions and concerns, as well as just running through a bit of a basic workflow and basic process to use for 3D printers in today's market.
And there will be another webinar later this week, I believe it's on Wednesday, which is going to address the 6 biggest concerns with using 3D printed parts, and that's going to take a deep dive into where 3D printing really shines and what we often find people's biggest concerns are whenever they ring up and talk to us about potentially moving to an additive solution. So that will be a good one, and that's on later this week.
That's great. Well, thank you very much for turning up and listening to us ramble on about printers for a little bit. And I hope you enjoy the rest of your day. Stay safe. Thank you.